Welcome to a lesson with Dr. Powell. We're going to look at the form that primes take on in a ring of integers of a number field k that lie over a rational prime p. We're going to assume that our prime p does not divide the discriminant of a power integral basis for this number field k. Now, this discriminant is the determinant of a trace form. Now, that trace form, just as a matrix, just with regular matrix multiplication, with like a column or something like that, actually represents an isomorphism between OK and Zn itself. And if we restrict this map to just Z alpha, then it's kind of like taking a map from Zn into itself, and the index of the image of doing something like that is just the determinant. In fact, we have the determinant right here of the image of Z alpha in Zn. This way is going to be equal to the determinant of this matrix, which is just the discriminant. So what do we get from that? We get that this index, the image of OK, let's see, the image of this in the image of OK is going to divide that index, so which is equal to the discriminant. And because f is an isomorphism, we get that the index of Z alpha and OK actually will divide the discriminant. And what we have is that if P doesn't divide this discriminant, then it definitely won't divide this guy. So how can you use that? Well, let's consider modding out by P and OK and modding out by P and Z alpha. Are these two ideas the same? Well, let's consider cosets over here. If we have something, I guess the question is are things in OK a multiple of P away from Z alpha? So is there a representative in Z alpha in every single coset? So every single coset, do we have an element of Z alpha? Then we could represent all of these cosets just by representatives in Z alpha. So we could kind of come over here. But then we have to check. If we have two different representatives and we want them to, and we subtract them, they should, if they are in, let's suppose that they are in the same, let's suppose that they're in the same coset of this, that means their difference must lie in here. But their difference also lies in Z alpha because both of them were in Z alpha. So the difference lies in this guy and in, so their difference lies in Z alpha, that is, and it lies in POK, but the intersection of those two sets is simply this one. And so what we see is all we need to know is that every coset over here has a representative Z alpha, and then we will have this isomorphism. That's all we have to check. Okay, which is the same thing as saying this is this set over here equal to this one, or is this abelian group over here with equal to this abelian group? Now, just keep in mind, we're not multiplying this all by OK. We're just simply looking at this ring right here added with this ideal. So these like two abelian groups. So we're kind of looking at indices of abelian groups now in some sense. So we know that the index of this guy in here, okay, that P will not divide it. Now, what about the index of POK in OK? Now, if we think about how the prime P splits or ramifies or however else in OK itself, in that analysis, what we actually see is that this right here, this index, and we don't go over it here right now, but this index right here on this side is a power of P. So wait a minute. So this index in here has to divide this guy and this guy. This guy doesn't have any P's in it, and this is only a power of P. And so the only option is for this index to be 1, which means these two guys are the same. Since these two guys are the same, then that guarantees this isomorphism. Okay, so with those being isomorphic, it will allow us to actually identify primes very nicely because we can use this isomorphism here. The minimal polynomial right here, because it's minimal, by minimality, makes that the representations over here as linear combinations of powers of alpha is unique. And that uniqueness actually gives us this isomorphism. Injectivity happens quite clearly because polynomials in X or alpha can be represented in both places, and then uniqueness gives us the injectivity that we need. So we have an isomorphism right here between these two guys. Between here and here, where we've modded out by the minimal polynomial of X. This is well-defined, a well-defined map, and it's isomorphic. Okay, so so if we mod out by P, it's kind of like modding out by P over here, which we can think of as modding out by this, modding out by the minimal polynomial mod P from this ring here, where we take the polynomials of coefficients in this finite field P right here, or FP. And by the Chinese remainder theorem, and we can kind of think of this as, well, as well, think of it as a direct sums here. Things kind of split. If we think about these, so this F1 to FR, so all these polynomials here as being irreducibles, mod P, or so we're going to, and then we end up getting this this nice decomposition right here. But we also, but let's look at it this way. The ideals in this quotient ring are going to be precisely those that contain this guy. So the ideals in here are going to correspond to the ideals that lie over P itself. And in OK. But over here, we're looking at ideals that contain this guy, which amounts, because this is a unique factorization domain and a PID, we can actually just get those prime factors by looking at the prime factors of, or the irreducible factors of this polynomial itself. And that'll correspond to the primes lying over P as we trace things back. In fact, tracing back, I mean, thinking of Fi as being bar, as being one of the irreducible factors, well, if we just lift that to anything in Zx that lifts up to it, and then just throw alpha into it, we actually end up getting, and then adding that by a multiple of P, as we trace maps backwards, we end up getting an ideal, and this ideal is a prime. And it lies, and this is a prime that lies over P, and all the primes that lie over P can be found in such a way. Thanks for watching.